Some 12,900 years ago, a profound and sudden shift occurred in the North Atlantic. Over the course of a single human generation, temperatures across northern Europe plummeted by an astonishing 10 to 15 degrees Celsius. The once green Sahara began to dry out, tropical rain patterns shifted across the globe, and ice sheets returned to lands that had been thawing for 2 millennia. Today, we know this event as the Younger Dryas. Analysis of ice cores and ocean sediments points to a single culprit: the collapse of the Great Atlantic Conveyor Belt. This history provides a sobering context for our present, as every major instrument monitoring that same oceanic system is now sending a clear and urgent signal. It is slowing. If this system could fail so catastrophically in the past, within a span as brief as a decade, it forces us to ask what the current data truly signifies for our future. These unfolding planetary stories are what we explore here on Calm Space. And we invite you to join us as we seek to understand them. Let us begin by picturing the Atlantic Ocean not as a static body of water, but as a colossal, hemisphere-spanning engine. This is not a metaphor, it is a functional reality. The Atlantic operates as a massive heat redistribution system, tirelessly pumping warm water northward and returning cold water southward in a continuous loop. One full revolution of this immense circuit takes roughly 1,000 years to complete. This planetary machine has a scientific name: the Atlantic Meridional Overturning Circulation, or AMOC. It is a system so fundamental to our climate that its workings are often taken for granted, yet its influence is felt every single day. The Europe we know today is, in many ways, a product of this powerful oceanic current. To appreciate its impact, consider that London is situated at the same latitude as Canada's Hudson Bay. This is a region of polar bears, where the ground remains frozen for 8 months of the year and the average January temperature hovers around -20 degrees Celsius. In a world without the Amoc, London, Berlin, and Paris would all share a similar, frigid climate. The reason they do not. The reason Norway can cultivate wheat at the latitude of southern Greenland is because of this oceanic engine. Western Europe is consistently 5 to 10 degrees Celsius warmer than any other landmass at its latitude, an incredible thermal subsidy delivered by the Amoc. This system has allowed for 12,000 years of continuous human civilization in the North Atlantic basin. Yet, a growing consensus from numerous peer-reviewed studies published within the last 5 years points to a deeply unsettling conclusion: this engine is failing. This is a statement so profound that it is worth pausing to consider its full weight. The single largest mover of heat in our planet's climate system, the very mechanism that built the stable environment of modern Europe, is faltering. This is not a projection for a distant future. It is happening now, measurably, and at a pace that is outstripping the forecasts of every major climate model. To understand why this system is now in peril, we must first explore its fundamental mechanics. The process begins in the equatorial Atlantic, where the relentless tropical sun warms the ocean's surface. As this water heats up, a second process is also at work. Here in the tropics, evaporation exceeds rainfall, meaning more water is leaving the ocean as vapor than is being returned by rain. This causes the salt to become more concentrated, creating a mass of water that is both exceptionally hot and exceptionally salty. This hot, saline water is then caught by the trade winds and pushed northward, forming the current we know as the Gulf Stream. The Gulf Stream is, in essence, the southern leg of the AMOC, and it carries with it a staggering amount of thermal energy, roughly 1.25 petawatts at its peak. To place that number in context, it is equivalent to about 100 times the total electricity generated by every power plant on Earth combined. Every second of every day, this immense, silent river of heat is driven north along the coast of North America by the Atlantic Ocean. But this heat does not remain locked in the water. As the warm Gulf Stream flows northeast toward Europe, it radiates its stored energy into the air above. The prevailing westerly winds, which have sculpted European weather for millennia, then carry this warmth over the continent. This is what creates Europe's famously mild winters, melting the snow in February instead of June. This is what made the agricultural revolutions of Northern Europe possible in the first place. A continent at the latitude of Hudson Bay simply cannot sustain itself without this continuous, permanent transfer of equatorial heat. The Amoc is the only system on Earth performing this transfer on such a scale. We now arrive at the part of the process that is most critical, as it is the very point where the engine appears to be breaking. By the time this water reaches the seas around Greenland, Iceland, Norway, and the Labrador Sea, it has released most of its tropical heat to the European atmosphere and has cooled dramatically. Herein lies the brilliant trick of ocean physics that powers the entire global conveyor. This water, now cold but having retained all of its tropical salt, has become the densest seawater on the planet. Cold water is dense and salty water is dense. Water that is both cold and salty is exceptionally dense, and it sinks with tremendous force. This sinking occurs in enormous columns, sometimes several kilometers tall, in a process oceanographers call North Atlantic Deep Water Formation. This is the pump. It is the driving force behind the entire global oceanic circulation. Without this sinking, the conveyor belt simply stops. The deep water that should be flowing south no longer does, which means the surface water is no longer pulled north to replace it. The entire loop breaks down. Once this cold, salty water has plunged to depths of 2, 3, or even 4 kilometers, it embarks on a slow, majestic journey southward through the abyssal Atlantic. It travels at depth past the equator and continues all the way to Antarctica, where it merges with the Great Antarctic Circumpolar Current. From there, this deep water spreads out into the global abyss, eventually rising back to the surface in the Indian and Pacific Oceans, ready to begin the long, slow return journey to the Atlantic. The entire circuit, from the surface to the abyss and back again, takes approximately 1,000 years. A single drop of water completes a full loop on a millennial timescale. This is the vast, slow, and powerful rhythm of the global ocean conveyor, a rhythm that has defined our planet's climate for eons. Understanding this timescale gives us a profound context for the rapid changes now being observed, raising the urgent question of what it means when such a monumental system begins to falter. For as long as human civilization has existed, a vast planetary engine has been operating in the background. It is a system upon which every empire, every city, and every farm in the Atlantic basin has been built. This engine has run so quietly and reliably that it has gone unnoticed, much like the heating system of a building you never inspect because you have always been comfortable. But now, that system is beginning to fail. In 2018, a paper published in Times Nature, one of the world's most prestigious scientific journals, brought this issue into sharp focus. A team led by Levki Caesar at the Potsdam Institute for Climate Impact Research devised an ingenious method to study the Atlantic Meridional Overturning Circulation, or Amoc. Because direct measurements of this current have only existed since 2004, the record is far too brief to distinguish a long-term trend from simple oceanic variability. So, Caesar's team searched for a unique fingerprint. They reasoned that if the Amoc were indeed slowing, the warm water it transports northward would fail to reach the subpolar Atlantic. This would cause a specific patch of ocean, located south and east of Greenland, to cool while the rest of the globe warms. After examining over a century of sea surface temperature records, they found it, a cold blob, sitting precisely where the physics predicted it would be, surrounded by unusually warm waters along the Gulf Stream. Using this fingerprint, they reconstructed the Amoc strength back to the 1870s, and their findings were sobering. The current has weakened by approximately 15% since the mid-20th century, and is now in its most fragile state in at least 1,000 years. That same year, a separate study offered an even deeper look into the past. A team led by David Thornley from University College London and Woods Hole Oceanographic Institution used a different kind of archive: sediment cores. These columns of mud, extracted from the floor of the Labrador Sea and the deep Atlantic, contain a layered history of the climate, stretching back through the entire Common Era. Within these layers, the size and shape of silt grains and the fossilized remains of microscopic foraminifera tell a story spanning 1,600 years. The conclusions from this paper were even more startling than Caesar's. According to the story written in the mud, the current weakness of the Amoc is unprecedented in approximately 1,600 years. The last time the Atlantic conveyor moved this sluggishly, Roman emperors were still being crowned and the Western Roman Empire was in the process of collapsing. The sediment record suggests that the Amoc is now in a weaker state than at any point since that distant era. It is a profound realization to see our present moment reflected in such ancient history. This is the system we are talking about. It is the silent engine that has underpinned every European harvest, influenced every American hurricane season, and shaped every African monsoon for as long as anyone can remember. And now, we have confirmation from 5 distinct research teams, using 3 different methodologies and over a century of data, that this critical system is failing. This convergence of evidence leads to an obvious and unsettling question, the one that every observer must now be asking. If the Amoc was the engine that helped build modern Europe, and it is now weaker than at any time since before the fall of Rome, what exactly happens next? The answer, it seems, is hidden within a patch of ocean that is behaving like no other on the planet. It is a region that is actively getting colder. Imagine a satellite map showing global temperature anomalies, a type of image you have likely seen many times. Red indicates where the ocean is warming, blue where it is cooling, and neutral colors where little change is occurring. If you were to look at such a map covering the satellite era from the late 1970s to the present day, you would see a very clear picture. The entire planet appears to be bathed in red. The Pacific is red. The Indian Ocean is red. The South Atlantic and the Mediterranean are red. The tropical oceans are red. Even the Arctic, especially the Arctic, glows the deepest shade of blood red on the map. Every ocean basin on Earth is warming at a rate that is unmistakable in the satellite record. Every ocean basin, that is, except for one. There is a single place on the entire planet that is bucking this global trend. Located just south of Greenland and Iceland in the subpolar North Atlantic, there is a roughly oval-shaped region of water about the size of Western Europe. On the temperature anomaly map, while everything else is red, this patch is blue. It is colder now than it used to be, with some areas showing significant cooling. This cold blob, as it has come to be known, has been a continuous feature in the satellite record since the late 1970s, and its cooling trend has only deepened over time. Over the last 2 decades, scientists have meticulously investigated every plausible explanation for why this specific part of the ocean would defy the global pattern. They have examined changes in cloud cover, shifting wind patterns, and local ocean mixing. Yet, one by one, each alternative explanation has proven insufficient. There is only one hypothesis that perfectly aligns with the geographic location of the cooling, its magnitude, its timing, and the fundamental physics of how heat moves through the North Atlantic. The Amoc is slowing down. As a result, less warm water is reaching the subpolar Atlantic, and the ocean surface in that region is not warming as it should be. Here, the story takes a turn that might send a small shiver down your spine. The fingerprint of a slowing Amoc is not merely a cold blob south of Greenland. The complete signature is a cold blob in that location, surrounded by anomalously warm water along the path of the Gulf Stream. This is because if the Amoc slows, the warm water that should be flowing past the Gulf Stream and on toward Europe gets held back. It accumulates in the western Atlantic, just off the coast of the United States, causing that region to warm with unusual speed. This creates a very specific dipole pattern, a cold patch over there and a hot patch over here. It's a kind of climatic ink blot test, where if you look closely, you can see the ghost of an ocean current that is no longer performing its function. This is the exact pattern that Caesar's team identified in their 2018 study. It is the same fingerprint that has been visible in the satellite record for half a century. And as the years have passed, this pattern has not faded. On the contrary, it has become sharper and more defined. It is worth pausing here, because this is the point in the narrative where the science itself begins to feel tangible, as if it were whispering over your shoulder. We are no longer looking at a model projection or a computer simulation. We are looking at direct, sustained observations of the Earth system unfolding in real time. For half a century, we have been collecting daily photographs of the ocean's surface from space. These images, free from any model-based assumptions, reveal a distinct regional pattern of temperature change, a pattern that cannot be explained by any other known mechanism within our climate system. This feature, known as the cold blob, is not a fleeting anomaly. It has been a continuous presence, acting as a clear spatial fingerprint of a weakening Atlantic conveyor belt. There is an almost poetic quality to this discovery. The ocean is presenting us with a clue in a location where none was expected, and in a shape that points to a single, specific cause, much like a lone set of tracks in fresh snow that could only belong to one creature. And yet, the cold blob is far from the only piece of evidence. Once scientists understood what to look for, these telltale signs began appearing everywhere. Over the past several decades, the Gulf Stream itself has been observed growing warmer and shifting its path northward. This is precisely the behavior one would anticipate if the warm water is no longer being pulled as efficiently toward Europe. The boundary separating the cold Labrador Current from the warm Gulf Stream has been moving, allowing subtropical foraminifera, tiny shelled plankton, to appear in Labrador sea sediments where they have no business being. Farther south, the Atlantic's intertropical convergence zone, a band of equatorial rain that governs the Sahel's monsoon, has been slowly migrating southward, just as models predicted would happen if the ocean's heat transport across the equator were to weaken. There is another consequence that may feel more immediate to many. Along the east coast of the United States, in cities like New York, Boston, Norfolk, and Charleston, tide gauge data from recent decades reveals an alarming trend. Sea levels in these areas are rising at a rate 3 to 4 times the global average. This is not a minor statistical variance. It is an enormous anomaly that demands explanation. The standard scientific reasoning for this involves a 3-part model. A portion of the rise comes from thermal expansion, the simple physical principle that warmer water occupies more space. This effect is more or less uniform around the world. Another part is due to land subsidence, where the ground itself is sinking because of local geology or groundwater removal. This factor is specific to certain regions, but is well understood. The third component, however, is the one that closes the gap between the East Coast's accelerated rate and the global mean. This component is attributed to ocean dynamic effects, driven by the weakening of the Amoc. As the circulation slows, water that would normally be pulled across the Atlantic begins to accumulate along the ocean's western boundary. This piled up water has to go somewhere, and its only direction is up onto the coast, into the streets, and past the sea walls. If you reside in one of these cities and have watched the king tides climb higher each year, or seen Norfolk's flood maps being redrawn every 5 years, or noticed Miami flooding on sunny days without a storm in sight. You have been witnessing the physical expression of this weakening. It is not a hypothetical future threat, but a present-day reality, recorded by every tide gauge from Maine to Florida. The evidence extends across the ocean. The unusually cold winters that struck northern Europe in 2009 and 2010, the severe cold snap of 2017 and 2018, and the persistently cool, grey summers in the British Isles during the early 2020s have all been linked by researchers to the influence of the cold blob and the erratic jet stream behaviour that accompanies a weaker AMOC. Of course, it isn't as possible to attribute any single weather event directly to climate change in a strict sense. One cannot say a specific blizzard was caused solely by the slowing circulation, but the collective pattern, the way Northern Europe's climate has begun to diverge from a simple, uniformly warming planet, is entirely consistent with the regional signature that the physics predicts. People in the United Kingdom are now living in a climate that is subtly different from that of their grandparents, not just warmer, but stranger and less predictable, with unusual cold spells that the rest of the warming world is not experiencing. When we step back and look at the full picture the data is painting, a remarkably coherent story emerges. We see a cold patch where there should be warmth. We see a shifted Gulf Stream, displaced plankton, and a migrating equatorial rain belt. We observe anomalously rapid sea level rise along the entire eastern seaboard of the United States and unusual cold snaps in northern Europe. Every one of these disparate signals is consistent with a single, unifying cause: a weakening Atlantic meridional overturning circulation. If this were a detective story, the pattern of clues would feel almost too perfectly arranged. The ocean is leaving its fingerprints everywhere, in space, in ancient sediments, in coastal floods, and in the pixels of weather satellites. The fundamental question is no longer whether the Amoc is weakening. The scientific community reached a consensus on that years ago. The urgent questions now are about the rate of this decline and its proximity to the kind of abrupt, non-linear behavior that the paleoclimate record warns us this system is capable of. If the cold blob is indeed the fingerprint of a slowdown, it means the ocean has been signaling its own transformation in plain sight for half a century, on every weather map ever produced. It seems we have only just begun to understand what it has been writing. If this is the story being told by the ocean's surface, an obvious question follows. What is happening in the abyss below? What can be said about the part of the conveyor belt that cannot be photographed from space? For that is where the true engine of this vast system resides. And as it happens, there is precisely one set of instruments on Earth that has been measuring it directly, in real time, for the last 2 decades. This brings us to the Rapid Array, located at 26.5 degrees north. You should remember that number, 26.5 degrees north. This invisible mathematical line, stretching across the Atlantic from Florida to the shores of North Africa, is where a group of British, American, and international scientists embarked on an unprecedented project 2 decades ago. They decided to wrap a single line of latitude with instruments to continuously measure the actual mechanical strength of the Atlantic conveyor belt in real time. Their goal was not to rely on satellites, sediment cores, or temperature fingerprints, but to measure the flow of water directly. The unit oceanographers use for such immense flows is the sverdrup. 1 sverdrup represents a flow of 1 million cubic meters of water per second, a scale that helps us grasp the colossal forces at play. When scientists speak of the ocean moving at 17 sverdrups, the scale can be difficult to grasp. What they are describing is a current so powerful that every second 17 million cubic meters of water flow north past a given line. To visualize this immense volume, consider the entire Mississippi River. The Atlantic Meridional Overturning Circulation, or Amoc, pushes a quantity of water northward that is equivalent to roughly 1,000 times the Mississippi's flow every single second. In fact, the Amoc transports more water in a single moment than all the rivers on Earth combined manage to move in nearly a minute. This reveals the sheer planetary scale of the engine we are examining. Recognizing its importance, scientists began a concerted effort to measure this colossal system in 2004. The monitoring network is called the Rapid Moc WBTS Array, a name whose structure hints at the collaboration of the three distinct agencies required to fund it. RAPID represents the United Kingdom's National Oceanography Centre program. MOC is the designation for the U.S. National Science Foundation's project at the University of Miami, while WBTS stands for the National Oceanic and Atmospheric Administration's Western Boundary Time Series. Together, these programs maintain a chain of moored instruments stretching across the Atlantic at a latitude of 26.5 degrees north. This network is supplemented by pressure sensors on the ocean floor and a remarkably clever technique involving a transatlantic submarine telephone cable. This cable, crossing the Florida Strait, allows for measurement of the Gulf Stream's integrated flow by detecting the faint electromagnetic field generated as conductive salt water moves through Earth's magnetic field. When all this data is combined, it provides a continuous, real-time measurement of the water overturning across this latitude, 24 hours a day, for what is now more than 2 decades. And the results from the RAPID array tell a complex story. The long-term average transport has been calculated at approximately 17 sverdrups. However, the ocean is a dynamic and noisy place, exhibiting significant seasonal shifts and year-to-year variability. A single year of data, viewed in isolation, could suggest a flow anywhere from 12 to 22 sverdrups. But over the full 20+ years of this continuous record, a distinct pattern has begun to emerge. Specifically, a substantial weakening was observed between 2004 and 2012, amounting to a loss of about 3 sverdrups, a decline of roughly 15% of the total transport. This change was statistically significant, standing out even against the background of the ocean's natural fluctuations. In 2018, David Smith and his team published their analysis in Geophysical Research Letters, and their findings were sobering. They concluded that the post-2008 average strength of the Amoc, as directly measured by the RAPID array, is demonstrably weaker than it was before 2008. While the downward trend has not accelerated in the years since, it has also not reversed. As far as our direct measurements can tell, the AMOC has settled onto a new plateau, functioning at a level approximately 15% below where it was when we first began this intensive monitoring. It is a stark observation that raises profound questions about the stability of this critical system. It is important to acknowledge the healthy scientific debate surrounding what can be inferred from just over 2 decades of RAPID data. The Amoc is known to have natural cycles of variability that unfold over years, decades, and even centuries. In that context, a 20-year record is, in some ways, too brief to definitively confirm a long-term trend. Oceanographers like Susan Lozier at Georgia Tech maintain an honest and cautious position. The RAPID record by itself is consistent with 2 different possibilities. It could be evidence of a long-term, human-caused weakening, or it could simply be a phase of normal, multi-decadal variability that will eventually correct itself. The data alone cannot distinguish between these 2 scenarios. However, and this is a central theme of our story, the RAPID record does not exist in isolation. The fingerprint analysis from Caesar in 2018 and the paleoclimate sediment records from Thornalley, also in 2018, do not stand alone either. Each of these methods has its own inherent limitations, and any one of them, viewed by itself, could be debated. But the crucial point is that they are all converging. These disparate lines of evidence are all pointing in the same direction, a direction that aligns perfectly with what the fundamental physics of freshwater dilution and density-driven sinking would predict, given the astonishing rate at which Greenland is currently melting. There is also a second array that must be mentioned, known as OSNAP, which stands for Overturning in the Subpolar North Atlantic Program. Initiated in 2014, it is positioned much farther north than RAPID, in the very region where the crucial process of cold water sinking occurs. OSNAP provides a more direct view of the engine's core, and while its record is shorter, its findings have been consistent with the broader picture of a weakening circulation, particularly in the eastern subpolar gyre. The combination of RAPID at 26.5 degrees north, OSNAP in the subpolar region, the transatlantic Argo float network, and the satellite altimetry record represents the most comprehensive suite of ocean monitoring instruments ever focused on a single circulatory feature in human history. And every single one of these instruments is telling the same story. The Amoc, this vital planetary engine, is running more slowly than it used to. It is not a catastrophic slowdown, not yet, but it is a measurable and persistent one. And most critically, there is no signal anywhere in the observational data to suggest that this slowing is reversing. The RAPID array is the gold standard for direct measurement of the Amoc, and it stands as one of the great, unsung scientific instruments of the 21st century. It doesn't generate dramatic headlines or possess a flashy name. It is simply a string of yellow buoys and concrete-anchored moorings sitting quietly across the Atlantic, a silently humming submarine cable in the Florida Strait, and a dedicated army of scientists. These researchers pull the data every few months, crunch the numbers, and publish their findings in journals most people will never read. And what they have been telling us, patiently and persistently, year after year, is that the largest heat engine on planet Earth is, in fact, slowing down. This is where the narrative takes a compelling turn, because it leads to the most obvious and urgent question. Why? What is actually causing this immense engine to lose power? The answer, it seems, is unfolding right now on a frozen island just north of the cold blob anomaly in the Atlantic. Here, ice that has remained stable for over 100,000 years is now sliding into the sea at a rate unlike anything science has ever measured. To understand the cause, we must journey to Greenland. Before we travel to Greenland, however, it is essential to spend a moment with a scientific paper that, more than any other in the last decade, dragged the AMOC story from a niche oceanographic concern into the heart of mainstream climate science. The world of science does not typically move quickly. Decades-long debates over methodology are the norm, but every so often, a paper is published that everyone, both supporters and skeptics, must take seriously. In 2018, two such papers landed within months of each other, fundamentally changing the conversation. Two separate lines of inquiry, both published in the journal Times Nature, arrived at the same profound conclusion. The first was a 2018 study from Levke Caesar's team, and the second came from David Thornley's. Working independently, these two groups achieved what the scientific community had been attempting for 3 decades. They successfully retraced the recent history of the Atlantic conveyor belt. Caesar's team approached the puzzle by looking for indirect evidence, much like investigators searching for the shadow of a person who is no longer there. Since direct measurements of the AMOC only began in 2004, they couldn't observe its past behavior directly. Instead, they focused on the consequences of that behavior. Using climate models, they simulated the Amoc at various strengths and observed the resulting patterns on the ocean's surface. This allowed them to identify a unique spatial fingerprint, a combination of the cold blob and the warm Gulf Stream pattern that changed in direct proportion to the overturning circulation's strength. With this fingerprint identified, they could examine the historical sea surface temperature record, which extends back to the 1870s, and translate it into a continuous estimate of the Amoc's power over more than 150 years. The results of this novel approach, published in 2018, were stark. The analysis revealed that the Amoc has diminished by approximately 15% since the middle of the 20th century. Statistically, the majority of this decline has happened since about 1985, a period that aligns perfectly with accelerating global warming and the increasing melt of Greenland's ice sheet. Perhaps most unsettling, the current strength of the Amoc, as inferred from this temperature fingerprint, is now weaker than at any other point in the entire observational sea surface temperature record. The data suggests this is not a minor fluctuation, but a significant and substantial departure from its previous state. In 2021, this conclusion was revisited and strengthened. Caesar, along with Stefan Rahmstorff and Nicholas Boers, all leading figures in this area of research, published a follow-up analysis in Time's Nature Climate Change. They expanded their work by incorporating additional proxies and more extensive datasets. The team ran rigorous consistency checks against multiple climate model ensembles, effectively testing their original findings from every angle, far from challenging the 2018 result. This new research confirmed it, and, if anything, made the conclusion even more robust. The message was clear. The Amoc is not merely weak, but weaker than it has been for centuries. Yet, the fingerprint method possesses an inherent limitation. It can only peer as far back in time as the reliable sea surface temperature records allow, which is to say, the late 1800s. To understand the Amoc's behavior over longer timescales, one must turn to the physical proxies preserved within the geological record itself. This is precisely where the work of Thorniley's team provided the missing piece of the puzzle. Thorniley and his colleagues at University College London and the Woods Hole Oceanographic Institution approached the problem from an entirely different perspective. They journeyed to the Atlantic and retrieved cores of mud from the deep ocean floor. It is worth pausing to appreciate the science of paleoceanography, a field that feels almost magical in its ability to read the past. The abyssal seafloor is a vast archive, a graveyard where a slow, continuous rain of dead microscopic organisms and tiny mineral grains settles year after year, century after century. In certain quiet locations, this sediment accumulates in such an undisturbed manner that it preserves a continuous, readable history, stretching back tens or even hundreds of thousands of years. By extracting a sediment core, one can slice it into layers and read history 1 millimeter at a time, holding 20 centuries of oceanic change on a piece of mud the length of your arm. Thorniley's team focused their analysis on two specific sites in the abyssal Atlantic, employing two complementary proxies. The first was the grain size of sortable silt found in cores from the Iceland basin. Sortable silt is a fraction of sediment particles within a specific size range that is highly sensitive to the speed of ocean currents. Faster bottom currents have the energy to carry larger, heavier grains, while slower currents can only transport the finest particles. By measuring how the grain size distribution changed through the layers of sediment, the team could reconstruct, century by century, the velocity of the bottom currents. Since these currents are driven by the Amoc, the grain size serves as a direct proxy for its strength. Larger grains meant a stronger circulation, while finer grains indicated a weaker one. The second proxy was derived from foraminifera. These are microscopic, single-celled organisms that construct intricate calcium carbonate shells. They are particular about their environment, thriving in specific zones of the ocean based on water temperature, salinity, and depth. When these organisms die, their shells fall to the sea floor, where they are preserved indefinitely within the sediment. By cataloging which species of foraminifera appear in the different layers of a sediment core from the Labrador Sea, scientists can reconstruct the past location of the boundary between the cold Labrador Current and the warm Gulf Stream. This boundary shifts north and south in response to the strength of the Amoc, providing another window into its history. Here, then, were two completely independent paleoceanographic proxies, one based on the physical speed of deep-sea currents, the other on the biological response to surface water temperatures. If both were faithfully recording the Amoc's strength, their stories should align, and they did, perfectly. Both proxies independently showed that the Amoc was relatively stable for most of the past 1,600 years, exhibiting only the natural, minor fluctuations one would expect over such a long period. Then, beginning around the year 1850, both records showed a substantial and persistent weakening. The Great Conveyor was slowing down. By the modern era, both proxies indicated that the Amoc's strength was at or near a 1,600-year low, the very same conclusion the fingerprint method had reached through an entirely different route. This was not a coincidence. It was a powerful corroboration. There is something deeply informative about the timing of that 1,850 inflection point. The year 1850 roughly marks the end of the Little Ice Age, a cooler climatic period that affected the Northern Hemisphere from about 1300 to 1850. The end of this era would have triggered a significant freshwater pulse from melting sea ice and shrinking ice caps across the high-latitude North Atlantic, exactly the kind of input known to weaken the Amoc. The historical context, the timing, and the mechanism all fit together. This makes the modern continuation of that weakening even more concerning, as it appears to be driven by the same process, but now fueled by anthropogenic warming rather than a natural recovery from a cool period. If we take a step back, we can begin to see what those twin 2018 papers truly accomplished in the story of our planet. Scientists reconstructed the behavior of a system that, before the mid-2000s, had virtually no continuous direct measurements. Using two completely independent methods to look back over 1,000 years, they found that both analyses agreed, leading to a sobering conclusion. The Great Atlantic Engine is in its weakest state in approximately 1,600 years. This isn't a model projection, but an empirical, peer-reviewed answer to where we stand right now. The concern was crystallized by papers from Caesar and Thornalley in 2018, followed by a wave of reinforcing studies. Caesar in 2021, Boers in 2024 using salinity proxies, and a study from Portman in 2026, suggesting models underestimate the Amoc's response speed. Underpinning this is the Deitlevsen 2023 paper, which applied tipping point mathematics to a potential collapse. 5 major papers from 5 different groups all converge on the same direction of change, building on the 2018 foundation. As the science matured, the central question shifted from times if times the system is changing to times how fast times and times how far times that change will go. The answer to how fast appears to depend almost entirely on a single factor: the volume of fresh water that continues to pour into the North Atlantic over the coming decades. This realization has sharpened the focus of an entire field of climate science. This brings our attention to the primary source of that fresh water, a frozen island the size of Mexico, located just north of the oceanic cold blob. This is Greenland, and it is bleeding into the ocean at a rate that has accelerated continuously since the early 2000s. Satellite gravity measurements suggest this colossal ice sheet may be nearing its own irreversible thresholds. Greenland is a place of immense scale, 2.5 times the size of Texas, with 80% of its surface buried under an ice sheet up to 3 kilometers thick. As the second largest body of ice on Earth, it holds enough frozen water to raise global sea levels by about 7.5 meters. For over 100,000 years, that ice sheet has remained in roughly its current form. surviving the end of the last glacial period and the Holocene climate optimum 8,000 years ago. For all of human civilization, it has been a stable, predictable feature of the climate. Yet right now, it is melting faster than at any point in the satellite record. Data from the GRACE and GRACE follow-on satellites provides a precise number through 2024, an annual loss of 270 to 280 gigatons, where a gigaton is a billion metric tons. Cumulatively, since 2002, Greenland has shed about 5,300 gigatons of ice, raising global mean sea level by roughly 1.5 centimeters from this source alone. The rate of loss has been accelerating. While 2023 was a year of lower net loss, and 2024 was less extreme than the worst on record, the overall downward trend has not reversed. Here we find the connection to the Atlantic circulation, where these threads join into a single chain of physics. The Amoc's engine depends on the efficient sinking of cold, dense water in the seas around Greenland, Iceland, and the Labrador Sea. This sinking process relies on water density, which is governed by two factors, temperature and salinity. The principles are simple. Cold water is denser than warm, and salty water is denser than fresh. Both of these effects are critical. In the modern North Atlantic, both properties are being altered. The ocean is warming, making it less dense, while also being diluted with fresh water, which also reduces its density. The sources of this fresh water are numerous. Greenland's ice melt at 270 gigatons per year. Arctic sea ice melt, with September extent down 40% since the late 1970s. Increased high-latitude precipitation and accelerating discharge from Arctic rivers. This river water flows from Siberia and Canada into the Arctic Ocean, then out through the Fram Strait between Greenland and Svalbard, directly into the region where the Amoc's deep water must form. The result is a freshwater influence on the North Atlantic, unprecedented in the satellite era. The very water that needs to sink to keep the Amoc running is becoming less able to do so. Each year, more fresh water forms a stable, less dense lid on the surface that resists mixing. This mechanism is not theoretical or contested. It is the same process that drove past abrupt climate transitions, including the Younger Dryas. While the Younger Dryas is a crucial historical analogue we will return to, the immediate point is clear. Greenland is the proximate driver. An ice sheet stable for 100,000 years is now bleeding into the exact ocean region that evidence suggests is approaching a tipping point. The Amoc's weakening trajectory, seen in all our data, is precisely what you would expect given Greenland's measured melt rate. The consequences are not abstract. We already observe the upper layers of the North Atlantic freshening. Observations are already revealing slowdowns in the formation of both Labrador seawater and Denmark Strait overflow water, which are the two principal components that create North Atlantic deep water. At the same time, we have seen distinct changes in the circulation of the subpolar gyre. Every one of these measurements is consistent with the predicted effects of freshwater pouring into the ocean from the melting of Greenland. This is not a distant forecast. It is a process unfolding in real time, on a scale of mere decades. And within this story lies a feedback loop with genuinely unsettling implications. As the Atlantic Meridional Overturning Circulation, or Amoc, continues to weaken, the northward flow of warm water toward Greenland diminishes. On the surface, this might sound like a positive development, since warm water is known to destabilize glaciers and accelerate ice loss. The reality, however, is far more complex. The warm water that is prevented from traveling north does not simply vanish. Instead, it accumulates in the western Atlantic, contributing to higher ocean heat content along the eastern coast of the United States. Furthermore, this heat finds its way into Greenland's western fjords through subsurface channels, pathways that are not dependent on the strength of the surface current. All the while, the broader warming of the high Northern Hemisphere, amplified by a phenomenon called Arctic amplification, that has caused the Arctic to heat up at roughly 4 times the global average, relentlessly drives surface melt across the Pacific. Greenland ice sheet, irrespective of the Amoc's behavior. The result is a profoundly asymmetric feedback. A weakening of the Amoc does not necessarily slow the melting of Greenland, but the meltwater from Greenland directly weakens the Amoc. This creates a one-way amplification within the system. As Greenland's ice loss feeds the circulation's decline, the decline fails to shut off the sources of heat reaching the ice sheet. This loop threatens to run faster and faster until the cumulative pulse of fresh water pushes the entire system over an unknown threshold. The crucial question then is where exactly that threshold lies. The honest scientific answer is that we do not know with precision. Because we have never directly observed the Amoc crossing a tipping point, we lack a calibrated value for the amount of freshwater forcing required to make it flip. Our only certainty comes from the paleoclimate record, which shows that it has happened before, on multiple occasions. In fact, such collapses occurred more than 20 times over the last 100,000 years, during periods climate scientists refer to as Heinrich events and Dansgaard-Oeschger oscillations. Each of these past events was triggered by some combination of glacial freshwater outbursts and atmospheric changes, and each one produced abrupt, decadal-scale climate shifts across the Northern Hemisphere, with temperature changes ranging from 5 to 15 degrees Celsius. Critically, all of these events took place on a planet with a much larger total volume of ice than exists today. This means that a smaller fractional melt from a vastly larger ice sheet was sufficient to flip the system. We no longer have a 100,000-year-old ice sheet to draw upon for our fresh water. We have Greenland, and Greenland is currently losing 270 gigatons of ice per year, a rate that is accelerating. If we follow the math and assume this rate continues to climb on its current trajectory, Greenland could be losing 500 gigatons per year or more by the middle of this century. Cumulatively, by the year 2050, the ice sheet could have shed somewhere on the order of 15,000 to 20,000 gigatons of ice. This is a volume of fresh water that begins to look meaningful, even when compared to the scale of past Heinrich events. And unlike those ancient occurrences, this release is not happening over millennia, but over the course of decades. The chain of physical events is starkly clear. Anthropogenic greenhouse gas emissions raise global temperatures. The Arctic warms 4 times faster than the global mean. Greenland's surface begins to melt more aggressively, pouring 270 gigatons of fresh water into the North Atlantic each year. This influx freshens the ocean's surface, creating a buoyant lid that resists sinking. As a result, North Atlantic deep water formation slows, and the Amoc weakens. The fingerprint of this process is already visible in a host of indicators: in sea surface temperatures, in sediment cores, in direct measurements from oceanographic arrays, in sea level rise along the US East Coast, in the behavior of the jet stream over Europe, and even in equatorial rainfall patterns over the Sahel. All of these signals are detectable right now. The engine driving it all, the immediate cause, lies just to the north of where we are looking, bleeding into the ocean. So the question becomes, how much further can this process go before we cross a point of no return? In 2023, 2 scientists in Copenhagen confronted this exact question, using a mathematical framework designed to predict tipping points in systems ranging from collapsing ecosystems to financial crashes. They applied this tool, and the number that emerged from their model was a specific year, a year that, for many, falls within their own lifetimes. In July of 2023, a paper published in Times Nature Communications Times sent a tremor through the climate science community unlike few others. The authors were Peter Ditlevsen and his sister, Susanna Ditlevsen, working at the University of Copenhagen. Peter is a glaciologist and climate physicist, while Suzanne is a statistician. Together, they applied a powerful statistical technique known as early warning signal analysis to the long-term sea surface temperature record of the subpolar North Atlantic, the very same cold blob region we have been discussing. Their goal was to estimate when the Amoc might undergo a full collapse. The year they calculated was 2057, with a 95% confidence interval that stretched from as early as 2025 to as late as 2095. It is worth taking a moment to understand what early warning signal analysis truly is. Describing it as mere statistics makes it sound dry, but what it actually does is both strange and powerful. Imagine a marble resting at the bottom of a bowl. The shape of the bowl represents the system's stable state, and gravity ensures the marble always returns to the center if it is disturbed. If you give the marble a small nudge, it rolls partway up the side before settling back down. The speed of this recovery depends on how steep the bowl's sides are. A steep bowl means a fast recovery. A shallow bowl means a slow one. Now, imagine that the bowl itself is gradually flattening. As its sides become less steep, the marble's return journey slows down. Its movements become more correlated, because each nudge leaves it lingering near where it was pushed, instead of snapping back immediately. The variance of its position also grows, as the same nudge now sends it further from the center. Eventually, when the bowl is flat enough, a single moderate push can send the marble out of the bowl entirely. That moment is a tipping point. The mathematics of complex dynamical systems demonstrates that before a system reaches this point, you can detect the flattening of the bowl simply by observing the statistics of its motion. As a complex system moves toward a tipping point, two specific statistical signals tend to grow. The first is autocorrelation, which describes how much the system's current state depends on its previous one. The second is variance, a measure of the size of its fluctuations around the average. The presence of a steady, simultaneous increase in both these metrics is considered the statistical signature of an impending shift. This phenomenon, known as critical slowing down, has been observed and confirmed across a diverse range of systems, from ecosystem collapse and epileptic seizures to volcanic eruptions and financial market crashes. While the underlying mathematics are well established, the real controversy begins when these principles are applied to specific, real-world systems, raising questions about interpretation. It was this very method that researchers Peter and Suzanne Ditlevsen applied to the climate system. They examined the annual mean sea surface temperature records from 1870 to 2020 for the region known as the cold blob, a key indicator of the Atlantic Meridional Overturning Circulation, or AMOC. Their analysis revealed that both autocorrelation and variance had been growing with statistical significance, a pattern consistent with critical slowing down. Their interpretation was that the AMOC, as reflected by this proxy data, is nearing a critical threshold. To project this trend forward, they fitted a stochastic model to the data, which calculated the point at which the system would lose stability and transition. The model's central estimate for this event was the year 2057, with a 95% confidence interval spanning from 2025 to 2095. The year 2057 is a startlingly near-term projection, falling just about 3 decades from now. This is a future that many people watching this will likely live to see. It is a time when some will be in middle age, others will be retired, and many will be raising children who are not yet born. And yet, according to the central estimate of this peer-reviewed paper in Nature Communications, that is the year the Great Atlantic Conveyor Belt could enter a full-scale collapse. It is a finding that demands both our attention and our critical scrutiny. It is crucial to be clear about what this study does and does not claim, as the debate surrounding it has been intense. The Ditlevsons did not definitively predict a collapse in 2057. Instead, they produced a single statistical estimate, derived from one specific methodology applied to one particular proxy for the Amoc's strength, and this estimate carries substantial uncertainty. The paper has faced several technical criticisms. The cold blob temperature record, while extensive, is not a pure, direct measurement of the Amoc's flow, but rather a complex fingerprint influenced by numerous atmospheric and oceanic factors. Furthermore, the mathematics of early warning signals, though validated in some contexts, have been challenged when applied to climate time series of this nature, where the underlying signal is obscured by decades of natural variability and noise. The assumption that this past trend can be linearly projected into the future to pinpoint a tipping year has also been publicly questioned by some oceanographers, including leading scientists at the National Oceanography Center and NOAA. This paper, therefore, is not the final word on the matter, but rather one compelling piece of evidence within a much larger and more complex puzzle. Yet, it would be a mistake to dismiss it entirely. Even if one discounts the 2057 central estimate, arguing that the methodology is too aggressive, and even if that date is pushed back to 2070, 2080, or even 2090, the implications remain profound. The simple fact that a peer-reviewed analysis in a top-tier journal can produce a 95% confidence interval with a lower bound of 2025 is, in itself, a dramatic development. For 30 years, climate scientists have largely treated an Amoc collapse as a low-probability event, a remote possibility for the 22nd or 23rd century. The 2021 IPCC report, for instance, classified a collapse before 2100 as very unlikely, while also noting low confidence in that assessment due to model limitations. The Ditlevsons' work did not invent this concern. It gave a specific number to a worry that has been growing within the climate science community for years. Stefan Rahmstorff, a lead author on the 2018 Caesar study, who has researched the Amoc for 35 years, has publicly stated his belief that there is a greater than 50% chance of an Amoc shutdown in the middle of this century. He has described such a collapse as one of the most dramatic climate shifts in the last 100,000 years. Similarly, a 2021 analysis in Nature Climate Change by Nicholas Boers suggested the Amoc may have already lost stability. The point is not that one paper made a single, shocking claim. The point is that over the last 5 to 7 years, a significant cohort of senior, well-respected Amoc scientists has become collectively more concerned about the timeline. The Ditlevson paper, while controversial, aligns with this broader shift in scientific sentiment. So, let us hold that number, 2057, in our minds as we continue. Everything else we are about to explore, from the historical precedent of the Younger Dryas to the concepts of Stommel's bistability and the consequences for Northern Europe, the US, East Coast, and the Sahel, will ultimately circle back to the same fundamental question. Is this central estimate too aggressive, a worst-case scenario, or could it, in fact, be in the right ballpark? Have we been collectively underestimating, in our models and our policy planning, just how quickly this vital engine of our planet's climate can fail? There is only one way to truly ground a statistical projection for a system we have never witnessed collapsing in modern times. We must look to the past, to the last time it actually happened. To truly understand what is at stake, we must find the historical analog and see what the planet looked like on the other side of an Amoc tipping point. And we have such an analog, preserved in what is likely the most detailed record of an abrupt climate shift in Earth's entire geological history. It began 12,900 years ago, as the world was slowly emerging from the last ice age. The great continental ice sheets were in retreat, and North America was gradually being freed from its glacial grip. Then, something happened that hit Europe like a hammer, an event that would last for 1,200 years. Europe was emerging from the ice. Across the continent, a gentle warming was underway as sea levels rose, reclaiming coastlines that had been exposed since the last glacial maximum. For tens of thousands of years, the land had been frozen, but now, plants were beginning their slow, determined colonization. It was during this period of climatic recovery that the first waves of human migration into the Americas were likely taking place. For roughly 2 millennia, the Northern Hemisphere had been on a steady warming trajectory, gradually approaching the kind of interglacial conditions we recognize today. For any humans trying to survive in Northern Europe, life was improving. And then, in what amounts to a geological instant, the climate violently reversed, plunging back into the depths of an ice age. This dramatic event is known as the Younger Dryas. Its name comes from a small, white, Arctic flower, Dryas octopetala, a species that thrives in the cold conditions of the tundra. Just as the climate was supposed to be warming, pollen from this flower suddenly reappeared in European lake sediments, a clear signal that it was advancing southward again when it should have been retreating. The flower's return was a powerful indicator of a much larger shift. The entire tundra biome had reclaimed the landscape, bringing with it cold-adapted plants, insects, and mammals. Ice core chronologies suggest this climatic reversal happened with breathtaking speed, possibly in as little as 1 to 3 decades. The data from Greenland's ice core records is truly staggering. These records, taken from the GISP2 and NGI ice cores, are not theoretical models. They are direct physical evidence. They show that average temperatures in the Northern Hemisphere plummeted by an astonishing 10 to 15 degrees Celsius in mere decades. This intense cold period then persisted for approximately 1,200 years before the climate flipped once more, just as abruptly, into the modern warm period known as the Holocene, the very climatic state that has nurtured all of recorded human history. The Younger Dryas was no minor fluctuation. It represented 2 complete, rapid flips of the planet's climate system within a span of just 1,400 years. The leading scientific explanation, which is supported by a wealth of evidence from Atlantic sediments and North American lake records, points to a single, massive trigger. The theory holds that an enormous outburst of glacial meltwater, originating from a vast body of water called Lake Agassiz, flooded into the North Atlantic. This sudden influx is believed to have shut down the Atlantic Meridional Overturning Circulation, or AMOC, the ocean current system that transports heat northward. When the flow of meltwater eventually subsided and the ocean's salinity recovered, the Amoc was able to restart and the world warmed once again. To grasp the scale of this event, we must turn our attention to Lake Agassiz itself. It is one of those features of geological history that, upon closer inspection, reveals itself to be profoundly consequential. Lake Agassiz was a proglacial lake, meaning it was formed from meltwater that pooled at the southern edge of the retreating Laurentide ice sheet, the colossal glacier that covered most of Canada and the northern United States. As the ice sheet melted and pulled back, water collected in the depression left between the ice and the higher ground to the south. At its greatest extent, Lake Agassiz covered an area of about 440,000 square kilometers, making it larger than all 5 of the modern Great Lakes combined. This immense basin held a truly vast volume of cold, fresh water, contained only by a precarious dam of ice, waiting for its moment of release. That moment inevitably arrived. While the precise trigger is still a subject of scientific debate, the most likely scenario is that the southern edge of the Laurentide ice sheet retreated past a critical drainage point. This caused the ice dam to fail, and Lake Agassiz drained suddenly and catastrophically. the floodwaters may have surged through the St. Lawrence River system into the North Atlantic, or perhaps through the Mackenzie River system into the Arctic Ocean, which then flowed into the Atlantic. Regardless of the exact path, the result was the same. A colossal pulse of freshwater, estimated to be around 9,500 cubic kilometers, was dumped into the North Atlantic over the course of just a few decades. This ancient cataclysm offers a stark parallel to what is happening today, as melting ice from Greenland slowly adds fresh water to the very same ocean. The consequences of this freshwater pulse were immediate and devastating, a chilling example of the planet's interconnected systems. The cold fresh water, being less dense than the salty ocean, formed a cap on the surface of the North Atlantic. This layer effectively blocked the formation of North Atlantic deep water, the sinking process that drives the Amoc. Within decades, the northward flow of heat that had been warming northern Europe did not just slow down, it collapsed. Sea ice rapidly expanded southward, the North Atlantic drift current dissipated, and air temperatures over Europe plummeted. The effects cascaded across the globe. The Sahara, which had been relatively moist, dried out. The vital African and South Asian monsoons either weakened or shifted south, and tropical rainfall belts, including those that feed the headwaters of the Nile, were completely reorganized. The climate then settled into this new, cold state and remained there for 1,200 years. To put this immense span of time into human perspective, 1,200 years is longer than the entire history of the Roman Empire, from its founding to its fall. It is more time than has passed since the Battle of Hastings in 1066. It is longer than any continuous human empire in recorded history. For 12 centuries, the world was locked in a different climatic regime: a frozen Europe, a desiccated Sahara, and weakened monsoons. It was a climate utterly unlike the stable one in which humanity built cities and developed agriculture. Then, just as suddenly as it began, it ended. The Amoc restarted, the climate flipped back, and the Holocene, our warm and forgiving interval, commenced. Yet, the Younger Dryas is not the only such event in our planet's recent past. It is simply the most recent, and the one we have been able to study in the greatest detail. Looking further back into the paleoclimate record, ice cores from Greenland reveal a recurring pattern of similar disruptions. These are known as Heinrich events, named after the German marine geologist Hartmut Heinrich, who first identified their sedimentary signature in the deep Atlantic. These events were characterized by massive armadas of icebergs, breaking away from the Laurentide ice sheet and drifting into the North Atlantic. As they melted, they released enormous quantities of freshwater and sediment into the very same patch of ocean where the Amoc's engine resides. During the last glacial period, there were 6 major Heinrich events, designated H6 through H1 in chronological order. Each one of these is associated in the climate record with an abrupt and dramatic transition. They consistently triggered sharp cooling across the Northern Hemisphere, while simultaneously causing severe disruptions to tropical rainfall patterns. This recurring pattern serves as a powerful reminder that the Earth's climate system possesses critical tipping points, and that the stability we enjoy today is not guaranteed. Each event is a natural experiment, demonstrating the profound sensitivity of global climate to changes in the North Atlantic. Superimposed on the pattern of Heinrich events are the Dansgaard-Oeschger oscillations, a sequence of approximately 25 swift climate shifts that occurred over the last 100,000 years. Each of these events followed a distinct rhythm: an abrupt warming phase lasting only decades, followed by a slow, gradual cooling over centuries or millennia, and finally, a sudden plunge back into cold conditions. The Greenland ice cores provide a stunning record of these fluctuations, revealing temperature changes between 5 and 15 degrees Celsius taking place in as little as a decade. While the precise cause is still debated, The prevailing theory points to disturbances in the Amoc, suggesting each oscillation represents the climate system flipping between different operational modes. The story told by this paleoclimate record is a deeply unsettling one. It reveals that the Atlantic meridional overturning circulation is not a system that responds gradually or predictably. Instead, it behaves like a system with multiple stable states. Over the past 100,000 years, it has violently switched between these states roughly 20 times. Every one of these flips triggered a dramatic temperature shift in the Northern Hemisphere, ranging from 5 to 15 degrees Celsius, all within a span of just 1 to 3 decades. In some instances, the planet remained locked in this new climate state for more than 1,000 years. This historical behavior forces us to ask a critical question. We are currently subjecting the Amoc to the very same pressure that the paleoclimate record shows can cause it to flip, adding enormous amounts of fresh water into the North Atlantic at an increasing pace. The possibility of a similar transition happening in our modern era is therefore not merely hypothetical. It becomes a question of our proximity to a dangerous threshold. The Younger Dryas event serves as a particularly stark comparison. That ancient event was triggered by a freshwater pulse from Lake Agassiz, estimated at around 9,500 gigatons, released over just a few decades. For context, the total freshwater added to the North Atlantic from the melting Greenland ice sheet since 2002 is approximately 5,300 gigatons, or 5,300 cubic kilometers. At the current rate of melt, we are only about 20 years away from matching the total volume of water released from Lake Agassiz. The crucial difference, however, is that our contribution is a slow, continuous infusion, not a single, catastrophic burst. Whether this distinction in delivery makes a difference is one of the most urgent debates in climate science today. An optimistic perspective suggests that the slow, steady release allows the ocean time to mix and adjust, suppressing deep water formation, but perhaps avoiding a catastrophic collapse. The pessimistic view, however, argues that it is the cumulative total of fresh water that truly matters. From this standpoint, the slow delivery is merely postponing an inevitable non-linear breakdown, similar to what the system experienced during the Younger Dryas. We simply do not yet know which of these interpretations is correct. The answer will likely emerge from the observational data gathered over the coming decades from tide gauges, deep-sea mooring measurements, and the ongoing analysis of sediment cores. The Younger Dryas stands as our primary historical analogue, a worst-case scenario. It shows us precisely what an Amoc collapse looks like, with the evidence etched into ice cores, lake mud, and ocean sediments in such detail that there is no ambiguity about the climate's response. This event exists in the geological record like a dark reflection, showing us a potential future that is not theoretical, but documented. If a pulse of fresh water from one melting ice sheet was sufficient to trigger it once, it raises the unsettling question of whether a similar pulse from a different melting ice sheet could do so again. Since the paleoclimate record proves the system can indeed flip, the most pressing question becomes, what determines the tipping point? What is the specific threshold of freshwater input, of overturning suppression, of the expansion of the cold blob that pushes the system from a recoverable slowdown into an irreversible shutdown? To begin to understand that threshold, we must turn to a piece of mathematics developed in 1961 by an MIT oceanographer named Henry Stommel. His work, a paper that was largely overlooked for 3 decades, has now become the foundational text for the entire conversation around climate tipping points. In 1961, Stommel published a brief but conceptually brilliant paper in the journal Tellus, titled Thermal Haline Convection with Two Stable Regimes of Flow. The paper introduced what is now known as the Stommel two-box model. It was a beautifully simple thought experiment involving 2 ocean basins connected by a shallow channel, with one basin representing the tropics and the other the poles. In his model, surface exchanges of heat and fresh water work to equalize the temperature and salinity of the two basins, while density differences drive the flow of water between them. When Stommel solved the equations for this system's equilibrium states, he discovered something remarkable. He found that for a broad range of external conditions, the system did not have one, but two stable solutions. In the first state, the water in the polar basin is denser, causing it to sink and drive a powerful overturning circulation that transports warm water toward the pole. In the second state, the polar basin's water is fresher and less dense. It no longer sinks, and the overturning circulation either collapses into a weak flow or reverses entirely. Stommel's model demonstrated that the system is bistable, functioning much like a light switch with two distinct settings, strong overturning or weak overturning. The shift between these states is not gradual but abrupt. Once a threshold is crossed, the system suddenly flips. For 30 years, the paper's profound implications went largely unrecognized. By the 1990s, however, as detailed evidence of the Younger Dryas and Heinrich events emerged, scientists realized Stommel's bistability was more than a mathematical oddity. It was the fundamental mechanism explaining the abrupt climate transitions seen throughout the paleoclimate record. The Amoc flips because the density structure of the North Atlantic inherently supports two stable configurations, and exceeding a freshwater threshold can force the system from one to the other. Yet, there is one final feature of Stommel's model that must be considered, and it is perhaps the most disquieting of all. The two stable states do not have a symmetrical relationship with the freshwater forcing that controls them. To trigger a collapse from a strong to a weak overturning state, the freshwater input must be pushed past a certain high threshold. However, to recover from that weak state and return to a strong one, it is not enough to simply reduce the freshwater back to its original level. Instead, the forcing must be brought down to a much, much lower point. This phenomenon is known as hysteresis. In essence, the system has a memory. The path out is not the same as the path in. The implications of this for our present situation are profound. It suggests that if the Amoc were to flip into its weak state, merely halting the melt of Greenland's ice might not be enough to ever flip it back. To reverse such a change, one would need to actively counteract the freshwater forcing, cooling the North Atlantic enough to refreeze vast volumes of ice. This would be necessary to overcome the system's newfound stability. On the timescale of human policy, such an intervention may be entirely out of reach. It suggests a chilling possibility that when this door closes, it locks behind us. This behavior, known as hysteresis, is precisely why a 2008 paper in the Times Proceedings of the National Academy of Sciences, Times by Lenton and his colleagues, identified the Amoc as a critical tipping element. Their framework was designed to separate climate systems that change smoothly from those that possess thresholds and multiple stable states. The Amoc was placed in the highest risk category, a group that includes the Greenland and West Antarctic ice sheets, the potential dieback of the Amazon rainforest, and a few other planetary scale systems. The defining feature of these elements is that once a threshold is crossed, returning is not a simple matter of reversing course. The push required to tip them over is far less than the pull required to bring them back. However, a central debate in climate science is whether the real-world ocean behaves with the same dramatic instability as Stommel's foundational model. Some of the latest CMIP-6 simulations, which inform IPCC reports, indicate that the Amoc may weaken steadily rather than collapsing suddenly. Yet, other analyses, including those looking for early warning signals, argue that precursors for this bistable behavior are already visible in our observational records. This disagreement represents the cutting edge of Amoc research, with a definitive answer not expected soon. In the face of this uncertainty, the policy conversation is guided by the precautionary principle, the idea that when the consequences of being wrong are catastrophic, you must act to avoid that outcome. If there is even a moderate chance of a Stommel-style instability, and the price is 1,200 years of glacial conditions engulfing northern Europe, the debate shifts. It is no longer a quest for scientific certainty, but a challenge of making decisions where the worst-case scenarios are almost beyond imagination. This brings the science to its most current and perhaps most unsettling point. In 2026, a paper was published in Times Science Advances, Times that has begun to change how the climate models themselves are being understood. This study, led by Christine Portman and her colleagues, is titled in essence, An Emergent Constraint on Amoc Sensitivity to Anthropogenic Forcing. If its findings are validated, it implies that the standard CMIP6 projections, the foundation for every IPCC report and government adaptation strategy, may be systematically underestimating how quickly the AMOC responds to a warming world. To truly grasp the significance of this result and what an emergent constraint is, we must first look at how climate modeling works in practice. Once the structure of the problem is clear, the paper's conclusion becomes all the more powerful. The modern climate models underpinning IPCC reports are known as General Circulation Models, or GCMs. These are monumental achievements, simulating Earth's atmosphere, oceans, and land surfaces on a three-dimensional grid spanning the globe. Grid cells can range from 100 kilometers down to just tens of kilometers across. The models solve fundamental equations of fluid dynamics and thermodynamics, stepping the system forward in time. Yet, for all their complexity, they are not perfect replicas of reality. A crucial challenge is that many vital processes, like cloud formation or turbulent ocean mixing, occur at scales far smaller than a model's grid. These processes must be parameterized, approximated with simplified equations, tuned to align with observational data. Because different modeling centers make different choices about these parameters, the world's 30 to 40 GCMs that contribute to the Coupled Model Intercomparison Project, or CMIP, do not produce identical results. They generate a range of projections for any given scenario, a multi-model spread that is a primary source of uncertainty. This spread in model outcomes has profound implications. For certain metrics, like the projection for global mean surface temperature, the models show a relatively high degree of consensus. But for other critical quantities, such as the strength of the Amoc, the disagreement across the CMIP6 ensemble is substantial. For the year 2100, under standard mid-range emissions scenarios, the projected weakening of the Amoc spans from roughly 20% to as much as 40%. This is not a minor discrepancy. A factor of 2 difference in the rate of slowdown translates into vastly different projections for impacts on northern European climate, patterns of sea level rise, and tropical rainfall. So, the critical question becomes, can we do better? Is there a way to use observational data to determine which of these models is more likely to be correct? This is precisely the purpose of a technique known as an emergent constraint. The core idea is to search for a statistical link across the entire ensemble of models, a correlation between a feature we can observe in the present day and a projected outcome in the future. If such a relationship exists, we can then use our real-world observations of that present-day feature to narrow the range of plausible futures. This powerful method was pioneered by Peter Cox at the University of Exeter and has been successfully applied to constrain uncertainties in everything from cloud feedbacks to the extent of Arctic sea ice. This is the exact technique that Portman and her team applied to the Amoc. They analyzed the CMIP6 model ensemble and identified a powerful relationship between the present-day pattern of Atlantic sea surface temperatures and the model's projected Amoc weakening this century. Specifically, models that simulated a more pronounced modern-day cold blob, an area of unusually cool water south of Greenland, alongside warm temperatures along the Gulf Stream, also tended to predict a much larger weakening of the Amoc by 2100. The correlation was robust enough to establish an emergent constraint. The final step was to bring in the real world. The researchers took the actual, observed pattern of sea surface temperatures in the North Atlantic and used it to see which of the CMIP-6 models, with their wide range of 20% to 40% projected weakening, were most consistent with reality. The result was deeply uncomfortable. The observationally constrained projection did not fall in the middle of the pack. It landed substantially toward the high end, suggesting that the most severe scenarios of Amoc weakening are the ones most consistent with the evidence we see today. The Portman result presents a sobering conclusion. If we treat the observed sea surface temperature patterns as a reliable guide, it suggests the Atlantic Meridional Overturning Circulation, or AMOC, is on track to weaken by approximately 50% by the year 2100. The confidence range for this projection is between 42 and 58%. This estimate is, on average, 50% more severe than the central projection from the CMIP-6 climate models, and it surpasses the upper-end predictions of most individual models. The implication here is profound. It suggests that the standard climate models, the very foundation for IPCC projections, government adaptation strategies, and regional impact studies for areas like Northern Europe, the US, East Coast, and the Sahel, are systematically underreporting how quickly the Amoc is reacting to a warming world. The discrepancy is not minor. It represents an underestimation by a factor of roughly 1.5 to 2. If the Amoc's sensitivity is indeed being so significantly misjudged, it follows that every projected downstream impact is also being underestimated. It is important to approach this with scientific care. The Portman paper is a single study, employing a specific methodology focused on a particular observed pattern. While the technique of using emerging constraints is powerful, it is not infallible, and the broader climate modeling community is still in the process of integrating this result. A fair interpretation is that the Portman study represents the leading edge of a new wave of analysis, suggesting that the central scientific forecast for Amoc weakening should be more aggressive than the IPCC's AR6 baseline. It points to the likelihood that the models the IPCC depends on are not sensitive enough to the effects of freshwater forcing in the North Atlantic. The full ramifications, whether other studies will corroborate this finding or if the next generation of models, CMIP-7, will incorporate these lessons, are still unfolding in the scientific literature. Yet, the direction of this correction is unambiguous. It does not point toward a slower, more gradual AMOC response, but rather toward one that is faster and more pronounced. When viewed through the lens of the Portman analysis, other alarming findings begin to seem less like outliers. The central estimate from the Ditlevsen paper, which proposed a full collapse as early as 2057, now appears less like a fringe possibility and more like a plausible mid-range scenario. Similarly, the 2018 discovery by Caesar of a 600-year low in the Amoc's strength seems less like a slowly developing trend and more like a system already deep within a regime of instability. The anomalous cold blob in the North Atlantic transforms from a passive fingerprint of change into an active and urgent warning. As you assemble these pieces of the puzzle in the order they were published, they all point in the same direction. The Amoc is weaker than the models predicted. It is responding faster than the models predicted, and it may be approaching, or have already entered, a state where the theoretical instabilities described by Stommel become a real-world risk. The consequences of this, varying by region and by economic sector, are set to be profound. So, let us explore what a 50% slowdown would actually mean in practice. This is not an abstract concept, nor is it a distant future or a work of science fiction. It is now within the central scientific expectation for the year 2100. It represents nothing less than a redrawing of the climate map for the entire Atlantic basin. Imagine, for a moment, a thought experiment. The year is 2100. The Amoc has weakened by 50%, in line with the Portman Emergent constraint. Greenhouse gas emissions have followed a moderate, middle-of-the-road pathway. The rest of the globe has continued to warm, on average, as projected by global mean surface temperature models. The critical question then becomes, what does this world actually look like? In northwestern Europe, the situation is peculiar. While most of the planet has become warmer than it is today, with the tropics growing dangerously hot and the Mediterranean becoming drier, a different story unfolds here. For the United Kingdom, Ireland, Norway, the Netherlands, Denmark, and Germany, the expected warming has not materialized in the same way. Winter temperatures, in particular, are not warmer than they are today. In some scenarios, they might be roughly the same. In others, they could even be slightly cooler. The reason for this anomaly is that the weakened Amoc has substantially diminished the northward transport of heat that historically kept these nations warmer than their latitudes would otherwise dictate. The cold blob has expanded, storm tracks have shifted, and the jet stream has become more volatile, leading to more frequent incursions of Arctic air southward over Europe. The result is a phenomenon some climatologists have termed regional cooling set against a backdrop of global warming. This is not a dramatic ice age scenario, but a 1 to 3 degrees Celsius offset against the global mean. Considering the rest of the world is warming by 2 to 3 degrees, this leaves northwestern Europe with a climate roughly equivalent to that of 2025, but with a critical caveat: increased variability. Brutal winters, like the one experienced in 2017 to 2018, would become more common. Persistently cool, grey, and wet summers, similar to the patterns seen in the British Isles in the early 2020s, would also become more frequent. This volatility would cause crop yields to fluctuate in ways European agriculture is not prepared for. Demand for heating fuel would remain high, even as the rest of Europe transitions to energy systems dominated by cooling needs. Furthermore, coastal storms would become more energetic, as the heightened temperature contrast between the cold subpolar Atlantic and the warming tropics drives stronger atmospheric pressure gradients, fueling more intense cyclones across Western Europe. In the United States, a different narrative unfolds. Along the East Coast, sea level rise accelerates beyond its already alarming pace. We have discussed how cities from New York to Miami are already witnessing sea levels rise at 3 to 4 times the global average rate. With a 50% Amoc slowdown by 2100, this anomalous regional rate would persist, and the cumulative effect would add another 10 to 30 centimeters of sea level rise by the end of the century. In some projections, this 10 to 30 centimeters is in addition to a global mean sea level rise of roughly half a meter to a full meter, depending on emissions trajectories and the behavior of ice sheets. When you combine the global rise with the Amoc-driven regional offset, you are looking at an East Coast that has experienced an effective sea level rise on the order of 1 to 1.5 meters by 2100. This reality would directly impact cities, including Boston, New York, Norfolk, Charleston, Savannah, Jacksonville, and Miami. The implications for coastal flooding, saltwater intrusion into aquifers, infrastructure resilience, real estate values, and insurance pricing are not abstract. They are immediate and operational. While cities are already redrawing flood maps and planning seawall projects, the acceleration of regional sea level rise driven by a weakening Amoc, turns what was once considered a manageable adaptation challenge into a much harder one on a much shorter timeline. In the tropics, the repercussions of a weakened Amoc are perhaps the most profound, yet they are often overlooked in mainstream Western discussions. The Amoc is responsible for transporting a tremendous quantity of heat from the Southern Hemisphere across the equator to the north. As this current falters, so too does this vital heat transfer. This disruption causes a critical shift in the Atlantic's intertropical convergence zone, or ITCZ, the equatorial rain band that governs the life-giving monsoons for both the African Sahel and South Asia. This band moves southward, away from its long-established position, a seemingly small change with devastating consequences. The Sahel, a vast semi-arid territory stretching from Senegal to Sudan, is entirely reliant on the ITCZ's location for its seasonal rains. A southward displacement of this rain band, by even a few hundred kilometers, could prove catastrophic for the region's agriculture. History provides us with sober warnings of this very phenomenon. During the Younger Dryas period, a similar ITCZ shift led to widespread drying across the Sahel. More recently, the African droughts from the 1960s to the 1980s, driven by natural variations in Atlantic sea surface temperatures, triggered a sustained southward ITCZ shift and resulted in famine across the region. Climate models consistently show that a 50% weakening of the Amoc would produce a shift in the ITCZ that is comparable to, or even greater than, these historical events. The implications for the approximately 400 million people living in the Sahel are difficult to overstate. With cascading effects on food security for West and North Africa, and even parts of southern Europe, areas that rely on Sahelian agricultural exports and would likely become destinations for climate-driven migration. The South Asian monsoon, which sustains nearly 2 billion people across India, Pakistan, Bangladesh, and Southeast Asia, is also tied to the temperature patterns of the North Atlantic through what are known as atmospheric teleconnections, though this link is more complex. A weakening of the Amoc generally tends to diminish the intensity of the monsoon in some areas, while altering its timing in others. While the precise net effect on agricultural output in South Asia is challenging to quantify, the scientific consensus points toward a negative outcome. It is a sobering thought that a change in the distant Atlantic could affect the lives of billions of people so far away. Across the global ocean, the consequences radiate far beyond regional climates. The vital fisheries of the North Atlantic, which thrive on the nutrient-rich upwelling and frontal zones created by the circulation, would face further disruptions and population declines. Cod stocks, which have already collapsed in areas like the Grand Banks and have struggled to recover, would be subjected to additional stress as warmer water species migrate north and cold-adapted fish lose their habitat. The migration patterns of Atlantic salmon would also be thrown into disarray. This bottom-up reorganization of the North Atlantic's marine food webs, a process already in motion, would only accelerate. In the Amazon, the altered tropical rainfall patterns and the shifted ITCZ push the rainforest closer to a trajectory of dieback. The Amazon itself is considered a tipping element in the Earth's climate system, and its fate is coupled to that of the Amoc. A weakening of the Great Ocean Current affects tropical Atlantic sea surface temperatures, which in turn influences precipitation over the Amazon, directly impacting the rainforest's resilience against the pressures of deforestation. A faltering Amoc therefore compounds the existing threats to the Amazon, elevating the probability that this vital ecosystem will cross its own tipping point sometime this century. This raises the alarming question of whether one tipping system can trigger the collapse of another. Meanwhile, in the Antarctic, the situation is genuinely strange. Some climate models provide evidence that a weakening Amoc, by reducing the northward flow of heat, actually leaves more warmth behind in the Southern Ocean. This excess heat could accelerate the melting of Antarctic ice shelves and contribute to the instability of the West Antarctic ice sheet. In this counterintuitive feedback loop, melting that begins with Greenland's ice could, in turn, hasten melting at the opposite pole. This would feed back into global sea level rise and further disrupt ocean circulation, demonstrating just how deeply interconnected the entire planetary system is. The dominoes, it seems, are arranged to tip into one another. The most honest summary of a 50% AMOC slowdown by the year 2100 is that it would result in a fundamentally redrawn climate map for the entire Atlantic basin. This is not the sudden deep freeze of the Younger Dryas, nor is it a Hollywood disaster film where cities freeze overnight. Instead, it is something more diffuse, and in many ways, more pervasive. It would be a slow, relentless reorganization of where rain falls, where major storms track, where coastlines flood, and where agriculture can be sustained. Our modern world, its cities, farms, fisheries, and even its insurance markets, was simply not designed to accommodate such a profound reorganization. And this scenario represents the central scientific expectation. It is not the worst-case outcome, but the middle case, the one that the leading edge of climate science currently anticipates happening on a timeline that includes the lives of most people hearing these words. If that is the median projection, then the worst case, a full, Stommel-style collapse with consequences analogous to the Younger Dryas, remains a tail risk. The question of how seriously to take that low probability, high-impact risk, and how much of it may have been kept from public view, is where we enter the realm of conspiracy and counter-narrative. Some of these theories are unfounded, but others point to genuine gaps in the public conversation. So, let us examine them. Whenever a subject like this enters the public sphere, a story of a tipping point in a vast natural system with potentially catastrophic outcomes on a timescale of decades, conspiracy theories inevitably follow. This is simply a feature of how high-stakes science is processed in our modern information environment. I want to walk through the most common conspiratorial framings, consider the strongest version of each one, and then explain what the science actually indicates, because some of these claims are easier to dismiss than others. The first claim is that information about the Amoc's weakening is being deliberately suppressed by governments and the mainstream media in order to protect the interests of the fossil fuel industry. The strongest version of this argument highlights the very real gap between scientific findings and policy responses. The IPCC has identified the Amoc as a critical tipping element, yet governments continue to approve the expansion of fossil fuel infrastructure. On the surface, this appears to be a clear contradiction. The rebuttal to this theory, however, is structural. Research on the Amoc is being published openly in the world's most prestigious peer-reviewed journals, including Time's Nature, Science, and their affiliates. It has been covered by every major international news organization, from the BBC to the Washington Post. The IPCC's sixth assessment report explicitly names the AMOC as a tipping element. There is simply no observable evidence of suppression. The information is not being hidden. The disconnect lies not in a cover-up, but perhaps in the political will to act on what is already known. There is a tangible gap between what science understands and what policy enacts. This disconnect, however, is a matter of political and economic will, not one of scientific censorship. The data is available for all to see. The crucial question is whether those in power are choosing to act upon it. This leads us to examine some of the alternative explanations that arise from this gap, such as the idea that geoengineering, including weather modification, HAARP, cloud seeding, and stratospheric aerosol injection is the true cause of the Amoc's weakening. To evaluate this claim, we must turn to the fundamental physics of the energy budget. The annual freshwater flux from the melting Greenland ice sheet, around 270 gigatons, injects an immense amount of energy into the North Atlantic, on the order of 10 to the power of 21 to 10 to the power of 22 joules per year, from the latent heat of the melting ice alone. In stark contrast, the combined energy output of every proposed and operational geoengineering project across the globe is estimated to be, at most, between 10 to the power of 15 and 10 to the power of 17 joules per year. This means the geoengineering signal is 6 to 7 orders of magnitude too small to be a credible driver of the Amoc's decline. Even in a hypothetical scenario where every cloud seeding program was perfectly effective and heart-performed feats it was never designed for, the numbers simply do not align. The observed forcing in the North Atlantic is fully accounted for by the melt rate of Greenland's ice, leaving no room in the energy budget for another primary cause of this magnitude. Another prominent concern is that the Amoc is on the brink of an imminent collapse within the next 5 to 10 years, a catastrophe that authorities are concealing to avert public panic. This narrative often points to a 2025 lower bound, mentioned in a confidence interval by Ditlevsen and Ditlevsen. However, a closer look at the science reveals a more nuanced picture. First, that 2025 figure represents the extreme low end of a 95% confidence interval from a single statistical analysis, a methodology that has faced scrutiny from others in the oceanographic community. The study's central, most likely estimate for a collapse is not 2025, but 2070. Second, our planetary monitoring systems, such as the Rapid and OSNAP arrays and the satellite altimetry network, would detect the clear signs of an impending collapse. Such an event would be preceded by a pronounced, non-linear acceleration in the weakening trend. Currently, the observational record shows a continued weakening at established trend rates, not the runaway effect expected before an imminent tipping point. The measured scientific position is that while an imminent collapse is a possibility that cannot be entirely dismissed, it is not the central forecast. More importantly, our observational systems are designed to provide warning before such an event would occur, making it a situation to watch closely, but not one to panic over. A different perspective suggests the weakening is not human-caused at all, but merely a feature of a natural rhythm, like the Atlantic multi-decadal oscillation or variations in the solar cycle. This view correctly observes that the Atlantic multi-decadal oscillation does create variability in North Atlantic sea surface temperatures over decades, and that the post-2004 rapid observational record is, by itself, too short to perfectly separate a long-term trend from this natural noise. But this is where the story from the past becomes essential. The rebuttal to this idea is rooted in paleoclimatology. Sediment cores, analyzed by Thornalley and his colleagues in 2018, provide a 1,600-year record of the Amoc's behavior, revealing that the weakening observed since 1850 is unprecedented, far exceeding any natural cycle visible in the proxy data. Furthermore, a 2018 study by Caesar directly tackled the question of natural versus anthropogenic drivers. It demonstrated that the spatial pattern of the so-called cold blob in the North Atlantic is inconsistent with a natural signature, but perfectly matches the fingerprint predicted by models of anthropogenic forcing. While internal variability is a real and important factor that creates noise in the data, it simply cannot account for a 1,600-year low. Conversely, there is the claim that the Amoc is actually fine, and that climate scientists are merely exaggerating the risk to secure funding or influence policy. Proponents of this view might point to instances where the scientific community has revised its own findings. For example, headlines in the early 2000s, based on a 2005 paper in Nature by Bryden et al., suggested a dramatic shutdown, a conclusion that was later substantially revised as more data became available. This is true, but it's a story of scientific refinement, not exaggeration. The 2005 result was based on a single snapshot measurement. When continuous monitoring from the rapid array, which began in 2004, provided a longer time series, the weakening trend was not eliminated, it was confirmed, albeit at a more moderate rate. Since then, subsequent analyses using paleoclimate data, fingerprinting techniques, and observational constraints have all converged on the same fundamental direction of change. The current scientific consensus is not the product of a single sensational paper, but the result of multiple, independent lines of evidence, all pointing toward the same conclusion. The narrative of exaggeration simply doesn't hold up when examined against the full stack of evidence. So, where does this leave us? The most honest assessment, based on a thorough reading of the scientific literature, is that the story of the AMOC is not a conspiracy, a cover-up, or an overblown crisis. It is, instead, a slow-motion emergency, well documented in open science with a timeline that remains genuinely uncertain. However, the central case implications are profound enough to justify the kind of emergency-scale response that the world has so far failed to mount. The frustration that fuels conspiracy theories is therefore not entirely misplaced. The chasm between what the science indicates and what governments are doing is undeniably vast. These theories simply misidentify the cause. The problem isn't censorship, it is policy inertia in the face of a well-understood planetary-scale challenge. And this brings us to the final, most important question, the one toward which all these lines of inquiry have been pointing. Every piece of evidence we have explored, the Caesar fingerprint, the Thornalley sediment cores, the rapid array, Greenland's gravimetry, Stommel's stability analysis, the Younger Dryas analog, Ditlevson's early warning signals, and the Portman emergent constraint is collectively trying to answer the same fundamental question. Are we, right now, in the process of crossing a threshold from which this vital system cannot recover? Are we, on the planet we inhabit, watching in real time as a critical tipping element begins to tip? Are the next decades of data going to show the slow, steady weakening of the past, transitioning into a non-linear, runaway collapse? Are we flipping the switch now? The most sincere answer, and one that requires careful framing to avoid misunderstanding, is that we simply do not know. This uncertainty does not stem from flawed science, concealed data, or some fundamental mystery that can never be solved. Instead, it arises from the very nature of the system itself. It is vast, slow-moving, and extraordinarily complex. Within this immense scale, the difference between a system approaching a critical threshold and one that has already crossed it is almost imperceptible on the timescales of our observations. The very signals that would confirm the tipping point has been passed are, by their nature, only visible once the transition is already underway and effectively unstoppable. This is the unforgiving reality of climatic tipping elements. They offer no clear announcement or advance warning. The moment the system shift becomes visibly apparent is the same moment that meaningful intervention becomes nearly impossible. The critical window for action, the period when mitigation could still avert the tipping point, is precisely the time when the threshold has not yet been observably crossed. By the time the change is undeniable, the opportunity has likely been lost. This means we are forced to act based on probability, on partial information, and on the converging signals from multiple independent lines of evidence, even when no single piece of data is conclusive on its own. The story these threads of evidence tell is a compelling one. The paleoclimate record confirms that the system is capable of flipping states. Modern fingerprinting techniques suggest the system is now in its most fragile condition in at least 1,600 years. Direct measurements from mooring arrays indicate a weakening of about 15% during the satellite era. Statistical analyses show the system is exhibiting the precursors to a tipping point, while emergent constraints reveal that our climate models have likely been underestimating its sensitivity. Furthermore, The accelerating melt of the Greenland ice sheet is increasing the very freshwater forcing that drives this weakening. While none of these points is definitive proof in isolation, together they form a powerful and cohesive chorus of warning. Within the scientific community, this chorus is not entirely unanimous, but the disagreements are more about the details than the fundamental direction. Stefan Rahmstorff, who has studied the system for 35 years, has suggested a greater than 50% probability of a shutdown by the middle of this century. Nicholas Boers has noted that early warning signals are already visible in salinity data. The Deitlevsen siblings' research points to a central estimate for a full collapse around the year 2057. In contrast, the IPCC's sixth assessment report deems a collapse before 2100 very unlikely, though it qualifies this with low confidence. Meanwhile, Christine Polman's work suggests that the CMIP-6 models may be underestimating the system's sensitivity by a factor of 1.5 to 2. The debate is a healthy one, focused on timing, magnitude, and the precise framework of bistability, but the consensus on the system's weakening is settled. Synthesizing this body of work, a more urgent picture emerges than what official projections might suggest. If one accepts the correction to model sensitivity proposed by Polman, the scenario of a 50% weakening by 2100 becomes not a worst-case outlier, but a central estimate. This would imply that the regional impacts on Northern Europe, the east coast of the United States, and the Sahel will be significantly more severe than what current adaptation planning accounts for. The probability of a full collapse within this century remains genuinely uncertain, perhaps somewhere between 5% and 30%. Depending on our emissions trajectory and physical thresholds, we have yet to fully understand. Yet, given the staggering consequences, even this probability is arguably large enough to justify an emergency-scale mitigation effort. The Deitlevsen's 2057 estimate, while perhaps too aggressive in its specific year and too narrow in its confidence, carries a broader message that aligns with the converging evidence. The window for collapse may very well be within this century, not the next. This makes the coming 10 to 20 years absolutely decisive. If the Amoc's weakening continues along its current trend, the central scenarios remain plausible, and we retain a window to respond. However, if this weakening accelerates, the timeline for a potential collapse could shorten dramatically. The conversation will shift if new monitoring systems, like the OSNAP array, the Abyssal Argo network, or next-generation satellite altimetry, detect non-linear behavior in the subpolar gyre. The answers we seek are written in the language of our planet's changing systems. If sea level rise along the US East Coast continues to accelerate in the next decade, it will be a sign of the fingerprint compounding. If Greenland's melt rates keep climbing, it is the freshwater forcing compounding. If the anomalous cold blob in the North Atlantic deepens or expands, it is the surface fingerprint compounding. Each of these signals offers a piece of the answer to the critical question. Is the system beginning to flip now? History and physics provide a stark context. The Younger Dryas event proves that such a flip can happen. The paleoclimate record proves it has happened many times before. The mathematics of complex systems proves that stable states can transition abruptly. Today, the evidence shows the system is in its weakest state in 1,600 years, while the Greenland ice sheet bleeds fresh water into the precise region of the ocean that has triggered these shifts in the past. The fingerprints, the cold blob, the warmer Gulf Stream, the rising sea levels on the east coast, the changes in Sahel rainfall are not theoretical predictions. They are visible now, on the planet we inhabit, in the climate we are living through. Whether the threshold is ultimately crossed in 2057, 2070, or 2120 does not significantly alter the moral calculus. Each of those years falls within the lifetime of people alive today. Each represents a future that is closer than the conventional climate conversation has prepared us for. and each carries regional and global consequences, for which the existing infrastructure of human civilization is profoundly unready. The honest, precautionary position is that even a low probability of an Amoc collapse this century is a risk too great to ignore. The consequences of misjudging an Amoc tipping point are comparable in their regional climate impact to a moderate nuclear exchange or a major asteroid impact. We do not operate our societies, our militaries, or our financial systems by assuming that events with a low probability but immense consequences are not worth preparing for. Yet, when the threat emerges from within the climate system, a process that is invisible, gradual, and named by an acronym most have never heard, we seem to treat it as background noise. It is not background noise. It is the largest heat-transporting machine on the planet, and it is slowing down on a trajectory that has the leading edge of climate science genuinely worried, all on a timescale that includes our own lives. When we ask the question, are we causing the system to flip right now? The only truthful response is that we cannot know for certain. However, a wealth of converging evidence makes it a possibility we can no longer afford to dismiss. We find ourselves within a critical period of agency, a window of time where a definitive threshold has not yet been visibly crossed. We are examining the fingerprints of a potential crisis, not yet standing over the final outcome. The essential question before us is whether we will choose to act based on these early warnings before we are forced to confront a far more irreversible reality. For the entire duration of human civilization, the Atlantic's great conveyor belt has been a constant, stabilizing force. It has been the silent partner in the rise of every empire along the Atlantic basin. Its influence has nourished countless harvests across northern Europe. Its steady rhythm helped maintain a climate that allowed for the flourishing of cities, the development of agriculture, and the very foundations of what we consider modern human existence. This system has been so profoundly reliable, operating so quietly in the background of our world, that for thousands of years, its existence went entirely unnoticed. But we see it now. We know it is there, and we know it is slowing. We also know that 12,900 years ago, when it faltered before, it did not do so gracefully. It collapsed abruptly, and the climate remained in that altered state for more than a millennium. Whether this history repeats itself is, in a very real sense, no longer a simple matter of physics. The fundamental physics of the situation will unfold according to its own laws. Greenland will continue to melt at a rate dictated by the global temperature we set. The North Atlantic will continue to be diluted with fresh water at whatever pace this meltwater pulse delivers. Consequently, the conveyor belt will continue to slow in response to this freshwater forcing. The only remaining variables, the only elements of this equation that humanity has any influence over, are the amount of carbon dioxide we continue to release into the atmosphere, the speed at which we can slow Greenland's melt by curbing global warming, and the urgency with which we build the monitoring systems needed to tell us in real time if that critical threshold is being crossed. These are the choices that remain for us to make. For the last half-century, the Atlantic Ocean has been sending us a message. It is written in the unusual cold blob anomalies appearing on temperature maps. It is inscribed in the changing size of sediment grains on the ocean floor. The message can be read in the tide gauge records all along the eastern seaboard and in the fossilized foraminifera discovered in the Labrador Sea. It is evident in the measured speed of the Gulf Stream, the diminishing thickness of Greenland's ice, the salinity of the subpolar gyre, and in the temperature data of every single pixel captured by our weather satellites. The letter's meaning is unambiguous. The engine is failing. It warns that it has failed before, with severe consequences. It reminds us that we are still within the window where a different choice can be made. But it also makes clear that this warning will not be sent forever. The letter simply asks us to look up. Some 12,900 years ago, this very ocean, in this exact region of the world, suddenly shifted from one stable state to another. A continent that had been gradually warming for 2 millennia was plunged into a deep freeze in less than 3 decades. That cold period endured for 1,200 years. Today, we are applying the same pressures to the same ocean system. The very pressures we know can trigger the same response. The question is no longer whether the climate system is capable of such a flip. The real question is whether our actions are causing it to flip right now. And the only honest answer is that we are witnessing its weakening in real time on every instrument we possess. The period in which we will discover the definitive answer is also, crucially, the only period in which we have any power to influence what that answer will be. To truly grasp the scale of what we are discussing, it is important to consider one final piece of perspective. In 1961, the oceanographer Henry Stommel, who first formulated the mathematics of this system's bistability, was working with little more than a pencil, paper, and a slide rule. He had no satellite data, no grace gravimetry, no rapid array, and no high-resolution sediment cores. He worked with a few decades of hydrographic measurements, the basic equations of fluid dynamics, and an extraordinary intuition for the behavior of oceans. From these limited resources, he developed a simple 2-box model that predicted, on theoretical grounds alone, the existence of a tipping point in the Atlantic conveyor. 6 decades later, technologies that were unimaginable in Stommel's time have confirmed his work. Satellites have measured the cold blob. Sediment cores have revealed the 1,600-year low in the current strength. Mooring arrays have directly measured a 15% weakening. Every single one of these modern measurements aligns with the theoretical framework that Henry Stommel laid down with pencil and paper in 1961. This is what genuine scientific consensus looks like. It does not form from a single press release or a panicked headline. It forms slowly, over decades, as multiple independent groups, using multiple independent methods, all converge on the same conclusion. It looks like a piece of mathematics from 1961, underappreciated for 30 years, and then a generation of oceanographers working quietly in places like Potsdam, Woods Hole, Southampton, and Copenhagen, who spent 6 decades building the empirical foundation that proved the theory was correct. The story of the Amoc tipping point is not one of sudden, shocking discovery. It is the slow ripening of a 60-year-old theoretical insight into a fully observed, real-world phenomenon. And we are the generation that has the privilege of witnessing this ripening. The depth of physical understanding of our climate system available to us right now is greater than at any point in human history. Our monitoring capabilities, our integration of theory and observation, would have seemed like science fiction to our parents' generation. The cold blob, the gravimetric measurement of Greenland's melt, the tracking of abyssal ocean currents, the mathematics of early warning signals, all of this is the inheritance of 6 decades of patient, quiet, and largely unnoticed work by tens of thousands of scientists. They have laid this picture down for us, piece by piece, paper by paper, year by year. The profound question that remains is what we will choose to do with this knowledge. So, look up, look at the ocean, see the persistent cold patch on the satellite map. Look at the tide gauge in the nearest coastal city. Consider the latitude of London and compare it to that of Hudson Bay, and reflect on the oceanic current that stands between them, creating 2 vastly different worlds. Watch the meltwater pouring off Greenland in real time on satellite imagery you can access on your phone in seconds. Observe the intertropical convergence zone creeping south. Examine the story told by sediment cores from the Iceland Basin and the Labrador Sea. The evidence is all around us, waiting to be seen. A remarkable consensus is emerging from the world's most prestigious scientific journals. Though their methodologies vary, they are all telling a single, consistent story. This raises a profound question. When the fundamental engine that has sustained human civilization throughout its history begins to power down, who will be aware enough to react in time? The next piece of evidence in this intricate puzzle, another telltale fingerprint, could already be approaching. Yet, upon its arrival, it will likely only be visible to those who have been diligently watching all along. For half a century, the ocean has been composing a message for us. The existence of this letter is not in question. The true uncertainty lies in whether it is being read in the halls of power where critical decisions are made. And can those of us who monitor the satellite maps, the tide gauges, and programming on channels like CalmSpace raise our voices loud enough to be heard before this message ceases to be a warning and instead becomes a dispatch from beyond a point of no return?